Hello everybody, my name is Walter and this is episode 69 of my Redstone Commands Series. In this episode I want to cover how you can use linear splines to approximate more advanced mathematical functions which are not directly available through the scoreboard command. So first of all, what are splines? Well, they are piecewise defined polynomials. So a spline can be in one area a linear function, and then following that you have a parabola, and then you have another linear function, and then maybe a polynomial of the third degree, and so on and so on. So they are a very effective way to approximate more complex functions by using very simple functions like polynomials. The simplest type of spline are using just linear functions, and that is what I want to show you today. Now, why would you want to use a spline? Well, similarly to lookup tables, they are highly customizable. They are also relatively simple and fast to calculate, especially since you're generally using low-degree polynomials. You also have the advantage that you don't have the limited, resolution as you would have with a lookup table itself. On the other hand, it can be non-trivial to fit the parameters of your polynomials to the actual function you want to approximate. And finally, and that is the primary issue with this approach, the word approximate already implies it a bit. You will likely end up with having some deviations or errors in comparison to the function you actually want to implement. And with that, let me show you how you can implement a very simple linear spline. Little warning though, the way I'm going to show you is the simplest way. It's not how you can minimize the deviations of your approximation. If you want to do that, then the math gets a bit more complicated, and I would recommend looking it up in the corresponding literature, since it very much depends on the actual situation or the actual function you are talking about. With that, let's get started with just 2 points. So the points are x1, y1 and x2, y2. If we now want to connect them with a linear function or a straight line, then we have the function for that, which is y equals a times x plus b. If we now put those 2 points into the equations, then we can solve it for a and b. And a is just the difference of the y coordinates divided by the difference of the x coordinates. And if we put that then in the equation, then we can very easily calculate b, which is y minus a times x for any of the points. So let's have a look at this in action. So let's simply have a look at the sine function of alpha in this case. I am selecting a few points on that graph, and then I just do the a and b calculations for each of those segments. And as you can see, it's a relatively good approximation, but there are also some spots where the deviation between the spline and the actual function is rather obvious. So in that case, it might make sense to maybe add another point at 30 degrees and 150 degrees and so on, if you want to have a better approximation. But for this example, this is good enough. And with that, it's time to show you how you can implement a spline with the example from just before using R.K.F commands. So I've split this into 2 functions. The first is the general setup and the call of the spline, and the second function is the spline itself. So let's quickly go through this. First, I'm setting or resetting my scoreboard objective and the display. Then I'm setting the input value to whatever I'm giving during the function call with a macro. And then with the sine being a periodical function, I do a modulo 360 operation. So I only need to calculate my spline for the area between 0 and 360. Everything else is not of import. So just writing the 360, then doing the modulo, and then cleaning up my temp value. And then finally I'm calling the spline. And with that, let's have a look at this function here. Now this file I've generated using an Excel macro I wrote for myself. If you're interested in that, let me know in the comments, and I might make an episode about this. But let's have a look at the function itself. So this is, as you can see, very similar to the lookup table from the previous episode. Just this time we have 2 commands per range. The first sets the a value, and the second sets the b value. A is directly written into the output value, which will be calculated a bit further later on, and b is written into the temp value. And once we have the corresponding values, it's time for the calculations. On a side note, if you haven't watched my episode about emulated fixed point operations, I would recommend doing this or you might get a bit confused in the following. So, but let's get started on the actual calculation. So first I need my scalar value since I'm doing a multiplication later on, so I need to rescale. Then I'm multiplying my A value, which is currently in the output, with my X value, which is the input value. So I now have A times X. Then I need to rescale, so I divide by the scalar. And then finally I add B to that, and that is already the implementation. Then I do just a little bit of cleanup. I don't need the temp and the scalar anymore in this case. And then and this is somewhat optional, return run, and then scoreboard players get the output value. This is just so that whoever is calling this function also has the chance to use, for example, an execute store command to directly write the result somewhere. And with that, it's time to show you this in action. So let's start with alpha 0. In that case, the output value we expect is also 0. And as you can see on the right side, input 0, output 0, this is exactly what we get. Shouldn't be a real surprise since, well, that is one of the points we've used in the first place to define the spline. So let's have a look at the point that is in between 2 points for our spline, 30 degrees. And in this case, we would expect a value of 1/2. But if we do this, you can see the actual result we get is 0.471. So that is what I mean with this is just an approximation and there will be some deviations. Now just to show you the modulo operation, let's say we have 1000 degrees and that gets calculated down to 280 degrees. And the output value we would expect is minus 0.985. And what we get is minus 0.978. So it's close, but not perfect. And then finally, in the other direction, minus 45 degrees gets calculated to 315, and the output is minus 0.708, and we would expect a 7 at the end. So there is a bit of a rounding error there, but we are at least very close. And with that, we've reached the end of this episode about linear splines. I hope you enjoyed it. I wish you a nice day, and well, see ya.